Ta-da! Happy Garbage Day to all who celebrate. The recycling truck had come by, but the garbage truck had not, so stay tuned for the conclusion of Garbage Day in Lisa's neighborhood. What do you remember from last time? Got some words up here to help jog our memory. Centering? Cluster means centering, yeah. So when do we need to do that? Or think about doing that? When we want an intercept to be meaningful, I would say that centering in general is when we want the intercept to be meaningful, but cluster mean centering is special. Do you remember what makes it special? The grand mean would be an example of what I call constant centering, in the sense that you're subtracting the same constant from everyone's score. And so grand mean centering is new and different. Question is, what makes it different? You can phone a friend too. Phone a friend. Okay, you've been phoned. What makes cluster mean centering different than grand mean centering or constant centering in general? That's the question. And you can phone a friend too if you want. It's fair. We'll just keep pushing it downhill. You're next, dude.
For real?
Yeah, for real. Okay, moving on down. What makes cluster mean centering different? Next.
Basically, instead of, when we talk about it in terms of like the smush slopes,
Mhm.
in terms of, instead of centering our variable based on the overall like population mean, if we're interested in cluster differences, it would be more useful to take the cluster mean, center around those, keep some of that difference as like valuable in our data.
Yeah, the key idea is that we're centering at the cluster mean of that variable, which makes it a variable that we're centering around, not a constant. That's the big difference. So we're reconfiguring what's in the level 1 predictor on purpose so that it contains only level 1 or level 2. You're on a roll.
Level 2.
The other one. Level 1, there we go. Yeah, we're taking the level 2 part out on purpose in cluster mean centering so that what's left is purely just level 1 within. And then we take that cluster mean, we center it at a constant, and then we put that in the level 2 model so that we understand that piece of variance as a complementary portion of the story. Yeah, so cluster mean centering is different than what you would have seen in any other context. I don't know that it exists out of the world of multi-level data. I can't think of an instance in which you would want to do something like that. How about at level 2? Are we going to cluster mean center anything at level 2? You're shaking your head? Shake it louder. No, we're not. Yeah, level 2 predictors are cluster things. So they're already, the only thing that we can center it around is a constant. There's no higher level that they could deviate from. So the distinction as to what happens when we cluster mean center versus constant center or grand mean center is a level 1 distinction only. What makes this tricky is that even though we're changing what goes into the model at level 1, it's going to be what happens at level 2 that changes across the versions. That's the tricky part. So that was where we started last week. What else did we talk about? Smushing? Do we want smushing? Not in this context. No. What's the smushed effect? I'll take gestures. I'll take words. Correct. This is the smushed effect. That's where the word came from. I Dream of Jeannie. That's what I feel like right now. It's an old show in the 50s. Look it up. What's a smushed effect? Okay, I haven't picked on this side of the room yet. It's your turn. One of the two of you. She's like, no, not me. You can preemptively phone a friend if you don't want to be called on. That's all right. Yeah, when a level 1 slope and a level 2 slope are essentially smushed together, meaning that they should each have their own relationship, but instead you've made them share one. That shared or constrained relationship is what I call the smooshed effect. What would someone who's not me call it? Conflated? That's my second choice. I like that one a lot. The other ones I think are a little more generic, but the key idea is that it's a misspecification where the level 2 model is more likely to be impacted. So we want to avoid that if possible. And so cluster mean centering is one way to avoid that. Grand mean centering after adding the cluster mean is a second. And there's a third that we won't get a chance to talk about very much, which is latent centering, which is turning the predictor into an outcome in a multivariate analysis instead. So let's see. I'm trying to figure out where would be a good place to pick up. Maybe talking about cluster mean centering, would that be good? Be a little more concrete? Maybe look at some data in an example? Okay, slides or data? Take your pick.
Data.
Data? Okay, data. Yes. Well, he was definitive, so you get what you want, sir. Okay, data. So we'll go through this in the context of data. This is the same data set that we looked at for example 2 from the high school and beyond, example in many different multi-level modeling textbooks, as well as in one of the articles on your reference group. So we have students at level 1 nested in schools at level 2 as the context, and quite a bit of schools. So 160 schools, that's a lot. Like that's way more level 2 units than I'm used to ever seeing. Like how many level 2 units would you see in your world?
I mean, you would like to see tens, like over 100 is very unfortunate.
So like you'd be happy with like 15?
Yeah.
Yeah. Mm-hmm. Yes, and I think Usman, in your project, you said students are clustered into classes, and you have maybe 12 of those.
Yeah, the max. Yeah.
Mm-hmm. Anyone else have?
Not on that.
Yeah, clustered data. How many clusters would you have in your data set typically? In the research that you're familiar with. How about therapists? 10 to 20. Okay, so we're in that same spot. If you're doing research on like healthcare outcomes or anything else that's measured at the state level, 50 states is the upper limit for what you can get, unless you start going to territories and other kinds of units like that. So yeah, 160 is kind of unheard of. That's probably why everyone uses this data set. So we are going to use it for today and then switch to a different one for the next example. So we have student level variables that we've added to the story. So previously we looked at the size of the school and whether or not it was public or private. In this example, we're going to look at level 1 predictors instead. So I have a quantitative measure of SES with a mean near 0 in this data set. Don't ask me for any other information besides that because that's it. And whether or not the student is white or non-white. That's all the level of detail they provided with that as well. So this example is going to use functions that I wrote to compute total R-square and pseudo R-square, as well as a function that computes the means of the clusters and adds them to the data set. So those additional pieces are in the R files online, and I will do as much of that as possible in Stata and SAS as well. So importing data and filtering so that we have complete cases, because that's going to happen anyway. Oh wait, this is a typo. I can see that's from my other example not being corrected. Let me fix that right now. Nope. I swear I can type. There we go. All fixed. I'll post the new version after class. So the first thing that I'm doing then is forming cluster means. And for Stata users, this could not be easier. It's one line of code. Lovely. So this not only computes a cluster mean, but it puts it in the same data set. So in this naming convention, I'm going with CM for cluster mean. That's sort of generic based on whatever level 2 units you have. So I have CM math as the outcome. Now, technically speaking, I don't need to form a cluster mean for this for my analysis, but I'm going to do it for descriptive purposes and pedagogical purposes as well. The cluster mean of SES, and then the cluster mean of a binary variable for whether or not the student is white as 0 or non-white as 1. So then what this is going to end up being is a cluster mean, just like the others, but we think of it as a proportion. So this would be the proportion of students at that school who identify as non-white, in which the lowest number you can have is 0 and the highest number is 1. Question, Vladimir?
Yes, Lisa. With eGen, do we have to do something with missing data?
I think it just uses whatever data it has, which is why to make sure that all the rows get included, I have this step first. Because otherwise you would end up with cluster means based on potentially a different subset of students, based on whether they have data for that variable or not. Yeah.
Okay, got it.
Yep, so this is a limitation of this strategy, is that for missing data, you kind of have to decide ahead of time what all variables are going to be in your story and filter based on that. And if you have a lot of missing data, this is a very bad idea. You should just not have missing data. That's the answer to that question, by the way.
Before we run the analyzing, should we make sure we have no missing data, little bit of missing data, or like how we can ensure our model will work?
I would probably look at some kind of correlation matrix that allows you to have pairwise correlations and see what the discrepancy in the ends is across combinations of variables, not just how many missing you have within a variable, because it's the combinations that are going to create a potential problem. Like if someone has one variable and someone has missing on the other, and then this person has it, like they're all going to get cut out of the analysis. What I would tend to do in real life, if I have a lot of missing data, is go straight to a multivariate analysis, where these become outcomes, in which case you don't have to filter for that. So that would be a full information maximum likelihood approach to this, by which we pretend the predictors are outcomes, but that's advantageous not just for missing data, but also in terms of dividing up the parts of the predictor into their level-specific pieces. That would be done better by the model than it would be by us as brute force. But brute force is where we're going to start. Okay, thank you for the question. Okay, so I'm doing descriptive statistics then at the school level for these variables. So in Stata, you can only have one data set open at a time. In the base data, I know there's a frames thing in which you can avoid that, but I don't know how to use it, and I don't know if we have access to that within the homework or the virtual desktop, so I'm going with this way. Collapse means to do this. Not to be confused with smushing, but this is also aggregating over rows. I can do that one. And then summarize is a descriptive statistic thing. PW core is pairwise core. So in Stata, if you just use core, then that does do listwise deletion, which we do not want on a general basis. And then restore means go back to that data set. And then I am centering the cluster mean for non-white at 0.3, which is going to be near the mean for the sample, so that that is a reference type of school. And then I am cluster mean centering the two predictors. So in my notation here, WC stands for within cluster. So that's my way of saying this is a purely level 1 variable. Cluster mean is going to be a purely level 2 variable instead. So it is original level 1 variable minus the cluster mean. And note that this is the uncentered version. So for instance, CM non 30 is the cluster mean of non-white centered at 0.3. I am using the original version as the centering variable here instead. Otherwise, you end up centering twice, essentially, and double shifting your intercept in a way that isn't necessary. And I'm also cluster mean centering our outcome math, just for the purposes of descriptive statistics for that. And then I printed a level 1 data set of summaries and correlations, and I will show you the R output for that in just a second. So, Stata folks, any questions about this code? All right. Well, if you think of any, let me know. R folks, there's a lot more of you. So, and R is harder, so that works out to be more questions potentially. So I have a list of all the packages that are being used. We're reading in the Excel data as usual, filtering to complete cases. This function add unit means, thank you Jonathan, does exactly what it sounds like. The key thing to make it work, though, I am told, is to make sure that the data set that you're taking the means of is the same data set that the means are going back to. Otherwise, it breaks. But that's what we want anyway, so to me, that's not really a limitation. So the unit variable is the level 2 identifier, and all of these are case and space sensitive, as indicated by the quotes. The mean variables are the ones that you're aggregating across rows, so math, SES, and non-white, and then the new names for those in the same order are adding the CM. I then created a level 2 data set using the unique function. Vladimir, how does that work exactly?
Unique,
Yeah.
take the unique element in those variables. Takes once each variable or row instead of all the rows from the original data.
Okay, so it
as
just,
far as I know.
it just grabs one, then it doesn't try to do that.
Yes.
Okay, so then school ID would be necessary so that we make sure we don't aggregate across schools in a way that's weird.
Yeah, because the information in those variables in your cluster means is the same across a school ID. One school ID will share the same value, so we need only one.
Need only one. Okay, got it. So then I have descriptives for those. So here's what the level 2 data then. So I have aggregated up to the school level. I have school mean math, SES, and non-white proportion. And I just want to give you a sense as to what the ranges of these variables are. So math varies on average between about 4 and 20. And SES varies, I don't know what that means. And non-white, of course, varies between 0 and 1. So one piece of foreshadowing that I want to point out here is that the slopes for this variable are going to look a little weird. Because slopes are usually per unit change in x, and in the scale of this variable, that is the entire range of possibility. Either you go to a school that has 0 students who identify as non-white, or a school that has 100% of the students identifying as non-white as the one. So per unit, this will look a little bit strange, but we have ways to solve that. So at the school level, just descriptively, these are the Pearson correlations among the school means. So CM math is a variable that we will not have in our analysis because that is essentially what the random intercept is supposed to be. At the school level, we have school mean differences in math. That's the level 2 outcome that's going to be predicted. This is the observed variable version of that. So the observed variable version says that SES and math are very highly related at the school level, and that math and proportion of students who are non-white are also related, but in the opposite direction. So these would be the level 2 types of slopes that we would expect in the between model. What makes schools different from each other? In math, part of the reason is going to be their average SES of their students, as well as the proportion of students who are non-white. And point 3 was around point 3 was the mean for non-white. The mean for cluster mean SES is already 0, so I left that one uncentered. So then I'm doing the same cluster mean centering process in R. I make the WC within cluster versions of these variables out of the original minus the cluster mean. And here are all of the variables that I created from the level 1 data set organized by construct. So I want to make the point here, like we have math, all right? That's our outcome. Math ranges from a minimum of about -3 to 25, whatever that means. Cool. Within cluster math, ranges differently. Within cluster math is U relative to your cluster's mean, whatever that happens to be. So it captures within school variation only. Consequently, it has a lesser amount of variance. So the variance in original level 1 math is 6.88. The variance in within school math is 6.19. So it's still mostly within school, but this difference is indicative of the amount of level 2 variation that would be hidden in here. And so cluster mean math, there's the standard deviation for that. And here's the range of those as well. Same thing for SES, within cluster SES, and cluster mean SES, and these ones. So we have less variability in the within cluster predictors and outcomes to the extent that we had cluster mean differences there in the first place. Now here's something interesting, to me at least. Of course, this is what I picked my research area to be, so it's like really interesting to me especially. But let's pretend like you're interested too. Can we do that? Okay, cool. So I have a correlation table here. This is new this year, by the way, TAs. You haven't seen this before. This was an idea that I had in the next example last year that I decided to bring into this one. So this is the level 1 data set, and I have it organized in terms of type of variable. So I have the 3 original variables in the story. Math is going to be our outcome, SES and non-white that are going to be our predictors. Then I have their within cluster purely level 1 versions, and then I have their cluster mean purely level 2 versions. So in research, we would typically report a table of correlations as part of our results, right? That's just a standard thing to do. Well, if you're doing a multi-level analysis, we need to think to ourselves, which correlations? Because if I just look at this little section right here, original level 1 variables. Math and SES are correlated 0.36. Wait a minute. Like 5 minutes ago, cluster mean math and cluster mean SES were correlated like 0.8. Likewise, math and non-white and the original variables are negatively correlated, as we would expect based on their level 2 counterparts, but not nearly as strongly. What did you say?
The other one was minus 5.
Yeah, minus like 0.5, right? So these are smaller. Now, if we go to the rest of the table here, let me see if I can make it fit on the screen. There we go. Here's the cluster mean centered versions of these things. So purely at level 1, if I subtract the cluster mean of math and I subtract the cluster mean of SES, so it's just, if you're relatively better at math than the other kids in your school, are you relatively more well off? And the answer is a little bit, correlation of 0.2. But at level 2, if you go to a school whose math scores are higher than other schools, then your school is likely to have higher SES kids in it to the tune of 0.8. So if we look at where these numbers would generalize to, hang on, trying to get the whole table on the screen at once. 0.8 and 0.23 are the level-specific relationships, but in the original variables, I get a correlation of 0.36 instead. Can you guess what happened? Is this correlation of the original level 1 variables, is this correct? Or is there some sort of problem with it? These are smushed correlations. Yeah, that's exactly what they are. So when folks are like, I want a table of correlations for my manuscript, I'm like, okay, which ones? Because 0.36 is essentially a weighted average of the within cluster relationship of 0.23 and the between cluster relationship of 0.79. Now there's a lot more kids than there are schools, which is why it's much more heavily weighted towards the level 1 relationship. But this is a smushed correlation. And so is this one, and so is this one. So if you are going to provide tables of correlations, which I think is a very reasonable thing to do, they should be level specific. I would report this section of the table only, and I would not report this section. Now there's a curiosity in my correlation table that we don't typically see, a block of zeros. These are among the cluster mean centered level 1 variables and the cluster means at level 2. Coincidence or consequence that they're all 0 right here? Consequence. Yeah, because things are not related across levels. A purely level 1 something cannot be related to a purely level 2 something. Like by definition, that would break the system. So cluster mean centering removes all of the level 2 information about the mean differences in your clusters from that level 1 variable. Therefore, it cannot relate to cluster mean anything. And that's the beauty of doing it. If you cluster mean center your level 1 variable, you know what it has to mean. It contains only level 1 within cluster student-to-student information. Your cluster means then contain the information at the school level, the cluster level in this example. So in your next homework, the one that the TAs are testing right now, I'm going to ask you to essentially build a table that looks like this and try to make inferences for yourself about what should and should not happen. But this is a general principle. You can see that the original level 1 variables are correlated with everything. As well they should be, because that's what was used to create the level 1 and level 2 parts. But level 1 and level 2 should be orthogonal. So thoughts or questions on that? Okay, you and then you.
Not really about the code, just in general. So, just thinking of when to know when to do this. Like when to know, okay, I need to check to see like the cluster mean centering, does that make a difference in my results? Like is it any time that anytime you're using a multi-level model and you have things measured, like you have level 1 and then you're concerned that there might be level 2. Like, I'm just trying to figure out when, like, is this something you should just always do? Or you check the ICC, oh, there's cluster differences, let's do this.
Yep, so repeat the question for the recording. When do I need to worry about this, broadly construed? And yeah, the answer is whenever you have multiple levels of variance in a predictor, it has a potentially different relationship at each of those levels at which it has variance. So step 1 is figure out what levels it has variance at. And so that's going to be the first thing we do, is not just empty means model for math, but we're also going to do it for the student predictors. And to the extent that their ICC is greater than 0, meaning they have some cluster something in it, we got to worry about this. Okay, question or comment?
Yeah, Lisa, just one question. Can you go back to the table with the descriptives, please?
Correlations or means?
Means, please.
Okay.
In that thing, we can see that the cluster means of the variables is the same as the mean of the original variables.
Mhm.
Is that a coincidence or consequence?
I believe it should work that way.
Always?
I hesitate to say always, but yeah, that's usually what ends up happening.
Because I'm thinking that in unbalanced case, but maybe here we have a pretty balanced clusters. But I thought that in some cases those two means should be different because it's not the same the mean of the individual values as the mean of the cluster means. So that's what I asked you.
Yeah, that's a good point. It seems like whenever we're doing observed variables that the means always end up matching. And if we're doing latent variables to try and get at the same process, that may not be the case because of correction for differential unreliability.
I
That
think so,
there
yes.
may be some wiggle because of that,
Yeah,
I think.
that's true, yeah.
But yeah, they should be pretty darn close though in terms of like what you would pick for a centering constant, for instance. Yeah. Yeah. Other thoughts, questions, comments?
For the correlation, are we just guessing for all the variables regardless of the binary variables?
So in this case, we are just estimating a Pearson correlation for a binary variable, which is not ideal. You could change it into some other kind of correlation, tetrachoric or polychoric or something that's more useful. But since the other variables in the story were quantitative, I just kept it alone. Is that the basis of your question? Did I hear you? Okay. Cool. All right. Other questions? Something happening over there. I don't know what it is. Any guesses? Someone walking on the ceiling? I don't know. Hey, pipe down over there. I can only cock so loud.
Prepare for the Halloween party.
Yeah. Let's see here. All right. Should we do an empty model? Wade back in? You guys are pros at this by now. So math is our outcome. What is beta OC? Do a little vocabulary review. What does it represent conceptually?
Fixed intercept.
Close.
Random.
Close. Yeah, this is the fixed intercept, gamma 0, 0. This is the random intercept. So if we put them together, that's what beta 0 is. It's the cluster-specific intercept that results from the average one plus the deviation for your cluster. So this is the variable that is being predicted at level 2. And it would be considered a latent variable in an SEM framework. I also call it a placeholder because it doesn't do anything more than contain these two pieces that we actually do care about. So beta 0C is each cluster's individual mean at this point, as built from the mean of the cluster means, plus how far off your cluster's mean is as the random intercept. So random intercepts have mean 0 because they're phrased as deviations from the fixed intercept. And then what's E? Very close. Residual. Not a variance, though. Yeah, this is a residual. Yeah. So E is a value for this person for this cluster, but it does get an estimated variance as a model parameter. So E is not a variance, but I would accept E is the idea that the model has a variance as part of it. I would accept that. So we have, let's see, I know I've alternated the output across programs here. Math on average is 12 in this sample, the mean of the cluster means. We looked at this before in the previous example, so I'm going a little bit quickly. The interclass correlation is 0.18. So that will be important to think about in terms of effect size. So 18% of all the data, the variance in math is due to what? ICC1 we're talking about. 18% of all the variation in math is due to level 1 or 2?
Then one.
Other one. 2. Yeah, it's due to cluster mean differences, which is what this random intercept variance is supposed to account for. So this is an effect size for how much dependency we have because students from the same school are correlated. Their average predicted correlation is 0.18 according to this model, which is pretty high for students in schools. So we're going to save this number and this number because these represent the starting points for adding predictors. And then we can see how much they each get reduced. And corresponding R code for that is right here, nothing that you haven't seen before. Now we're going to do the same process for the level 1 variables that are intended to be predictors. And I'm phrasing it that way on purpose. I don't care if conceptually you're thinking of a level 1 variable as an outcome or a predictor. The pre-processing steps that I'm showing you would be the same. We need to know how much variability is at each potential level in each potential variable to be able to set up our model to appropriately distinguish them. So it doesn't matter. Like if it's a predictor or an outcome, we still need to know this. How we know this is dictated by the form of the variable. So because SES is a continue-ish, as I would call it, or a quantitative variable, we can treat it the same way as math. So here's Stata code where SES is the outcome. And here's R code where SES is the outcome and R output as well. So in this case, here are the two variance components for SES. We have a mean of 0 for its fixed intercept, and we have an ICC of 0.27. So conceptually, what did I just find out? My SES level 1 student predictor has an interclass correlation of 0.27.
27% of the variance in SES is due to level 2 mean differences.
Exactly right. 27% of the variance in SES is due to level 2 school mean differences. So do I got to worry about cluster mean centering then? Yes, I do. Anything above 0, you got to worry about it. If it's very close to 0, then you might just cluster mean center your level 1 predictor and not do anything at level 2 because there basically isn't any level 2 variance. But in most cases with observed measured variables, it's going to have variance at level 2. And is that significant? Yeah. So if we do a model comparison of a model that does not have a random intercept to a model that does, then the models differ by 1 parameter for that random intercept variance. And that is what this little table is telling us. If we took out the random intercept for schools, this is how much the log likelihood would change. And this is the test statistic for that change. So what's the critical value? Anyone remember off the top of your head for a likelihood ratio test for 1 degree of freedom at alpha of 0.05? Anyone?
271.
2.71 with a mixture chi-square, yes, and with a regular one with 1 degree of freedom?
1.95.
3.84 in this one. Yep. So is this bigger than like 4? Yes. So we're good. I don't need to worry about the mixture distinction. So yeah, so far what we've learned, math as the outcome is 18% schools. SES as a potential level 1 student predictor is 27% schools. Now what about non-whites? That is a binary variable. Can I throw that in my regular mixed model equation? Well, will it let me? Let me ask you that. Will it let me? Will the software give me any errors? Nope. Is it a good idea? No, why not? I'm guessing I gave the answer away by saying, is it a good idea? Kind of a leading question. But I'm curious as to whether you can recognize why not. I'm talking about predicting a binary variable with a standard multi-level model. And you all said, sounds sketchy.
Add to the assumed distribution.
Yeah, what distribution are we assuming at level 1 for the residuals?
Normal distribution.
Yep, and can a binary variable have a normal distribution? What if I transform it? What if I take a log transformation? Can that fix it? No, no, it cannot. That's one problem. So we have the wrong distribution at the bottom. What should it be for a binary variable? This is a crossover event for the other classes. Starts with a capital B for a dude. B-E-R. N. O. Give me a U. Hey, there we go. Yeah, what we should have is, as if we were doing a logistic regression, predicting a binary outcome in a single level model, we would have a Bernoulli conditional distribution because Bernoulli has one parameter, the probability of a 1, that's it. And that one parameter dictates the variance around it. It's the probability of a 1 times the probability of a 0, which means variance is at a maximum at 0.5 and it shrinks as you go out. So non-constant variance is a consequence of a binary outcome that the normal distribution cannot handle. So it's not just the normal part, it's the constant variance part. Also, if this were a regular predictive model, could we have a linear slope predicting a binary outcome? Or would that maybe be not a great idea? I'm sorry, I can't hear you. We can't? Well, we don't have one right now, but I'm saying, what if we were going to try to predict this in a normal model? What are the problems? Yeah, and we're saying we can't have a linear slope? Or we can't? We can't, and why not?
I'm not sure. So you're saying if you are predicting a binary outcome, can we or can we not have a linear slope?
Yes, directly. And can we have a linear slope directly in predicting a binary outcome, or is that a not great idea?
No.
No, correct. What do we need to do instead?
We need to transform. Use a link function.
We need a link function. So yes, this is the world of generalized models, as they're known. We're picking up something called a link function, and we're switching out what the conditional distribution is. A link function is a transformation of the outcome to be predicted that places it into a continuous metric. That way we could have a linear slope. And they come in really two flavors for these models for binary variables, logit or probit. For the purposes of this class, we're going to go with logit and not worry about it. So a few of you, I think, have binary variables as part of what you're going to be doing for your project. This would be something that, if you aren't familiar with those models, that I can help with, but I at least wanted to give you an example to get started with here. So what we're going to do then, to ascertain the ICC for non-white as a binary variable, this piece right here, that is the log of the odds of the probability of a 1, which is being non-white in this example, otherwise known as the logit or the log odds.
You're missing the spell.
Can-
You used to have low.
Yeah, I don't, my stick's at home, and yours is upstairs in my office, so I do this conductor thing when I teach this. So this is the log of the odds of the probability of a 1. And I say it that way to walk us through all of the steps here. So we start with probability of a 1. Okay, that is continuous between 0 and 1. That's the conditional mean the model is trying to predict. We turn that into an odds by dividing by the probability of a 0. And that creates a skewed distribution that is bounded at 0. Then the last step, taking the natural log of those odds extends the left side of the distribution, so it's continuous until we end up with something that theoretically looks more like a normal distribution, but it's logistic. It's a little bit differently shaped. So then we have just beta 0 here. There's no E. And that's because E is not included to represent the idea of a separately estimated level 1 residual variance. In these models, it's going to be the constant 3.29 as residual variance. That comes from the use of a logistic distribution. It's a longer story than I have time to tell right now, but it's just a number that we're going to stick in there. I can give you stuff to read if you want to know where that came from. But level 2 is the same. So in generalized multi-level models, it's the level 1 distribution we change out. Level 2 is always multivariate normal. That's baked into the software. So I have the output from both packages here because this is a different routine to get this intraclass correlation. ME logit is what I'm using in Stata. That stands for mixed effects logit, so the multi-level version of logistic regression. It has a fixed intercept in logits, which you can back translate into probability if you want. And I have just the level 2 random intercept variance here. There is no separately estimated level 1 variance. As we saw before, the likelihood ratio test for a model without the random intercept is printed for you. It has a value of like 3,000, so I'm going to go ahead and say yeah. And the intraclass correlation, as computed using 3.29 for their level 1 residual variance, is 0.63. That's a lot. I saw your face like, what? Is it all the steps or the number that got you?
No.
The number, okay. Yeah, these data are real-ish, is what I would say, because the numbers don't quite math, but I'm guessing that they're based on like real data as an inspiration piece. But real or not, in this data set, 63% of the variance in students identifying as non-white has to do with what school they go to. So that we saw earlier foreshadowed in the descriptive statistics at the school level. I did not point this out then, but I should have. The range of students who identify as non-white at the cluster mean level is the full range of 0 to 1. So in this data set, there are schools with 0 students who identify as non-white and schools with 100% who do. There's a big difference here. So yeah, because SES has an intraclass correlation of 0.27, and because non-white has an intraclass correlation of 0.63, we got to worry about splitting out their relationships across levels of analysis. We got to worry about smushing, in other words, because we don't want to do that. In R, the code to do this model, we've been using what people call Elmer. I'm going to call this Glimmer. G-Elmer is what I think normal people would call it, but it looks like Glimmer to me. It wants to know what family of generalized models you're using. So in Stata, the logit package understands that that's what you want. This one, you have to tell it that explicitly. So it's the binomial family. Bernoulli as a distribution is a special case of binomial for one trial with the link equals logit. This refers to an option for estimation that I had to add to make the results match in Stata. And we get the same information close. So I just have an aside here. Before I added this piece to make it match Stata, here are the results that I got. They differ across packages much more so. So you will not necessarily get the exact same answers across packages for these generalized multi-level models, and I gave up trying on that a long time ago. But we come to pretty much the same conclusion, 0.62 for the intraclass correlation out of R as well. All right, and I have to do a workaround to get a likelihood ratio test because it would not let me estimate one model in Glimmer and another model in Elmer and do a likelihood ratio test for me. So I had to do it manually. So I estimated here a logistic regression using GLM, so taking out the random intercept variance. I then computed -2 times the difference in log likelihood for these two models, computed their difference, and then got a p-value for that, and here it is. So again, 3,000, good enough. All right. How are we doing, folks? Okay? Thumb check? Want to add some predictors? Okay, so we're going to do this the easy way first, and then we'll do this the hard way. Fair? Okay. So I am going to use the cluster mean centered version of SES and include a fixed slope for that as a level 1 predictor. Just one new thing at a time here. So note the notation. In my equation, I am trying to be very clear about how this variable has been centered. And I would highly encourage you to do the same in communicating your equations. So if we break this down here, beta 0c is still how each cluster is going to get its own intercept. Beta 1c is how each cluster is going to get its own level 1 slope for the effect of SES. Right now, beta 1c is just the fixed slope, so this is kind of unnecessary, but if we were to add more stuff to it, then it does become necessary to keep the beta 1 representation. Then I have the original SES PC. Is that a level 1 variable or level 2? 1. So PC means level 1, things that vary over persons and clusters. Then I have the cluster mean. Is this level 1 or level 2? 2. How do I know that from looking at the equation?
There's only the C.
There's only the C. Exactly. Yeah, don't overthink it. It's after lunch on a Tuesday. There's no overthinking. I'm just throwing out softballs here. It's fine. So this is saying I have taken my original person level SES and subtracted off the cluster mean. So a student who has a 0 on this new variable is at their school's average resources. They're average for their school. For their school is the critical part, though, right? Like if you go to a school with everyone's driving like Beamers and Lexuses and all those sorts of things, then maybe like your, what's an expensive car? Your Audi is like sort of mid, whereas if you like show up at my, with my car, my 2008 Corolla that I'm still riding around in, right? That would be a nice car to some people, and that would be a piece of crap at that school. So it's all relative. My car is paid for. My car is paid for, and it has 86,000 miles, and that is why I drive a car that is that old. I am taking that car with me, yes. It is going to make it to South Carolina, it is. Or I will just, it will die on the side of the road, and that will be the end of it, but I'm going to try. So that is my goal. My eventual goal is to give it to Hugh. He's 10. So can we make it another 5.5 years is the question. We'll find out, but it's in reasonably good shape. The worst part about it is that the underneath of it is like rusted out because of all the snow and corrosion. And like one day I was driving it and I heard this, like something started like dragging on the ground. So I had to drive it down to the car shop, like with the dragging on the ground the whole way. And they essentially just sort of like glued it back together with like some twist ties and rope and stuff. And they're like, if this breaks again, it's going to be really expensive. Like, okay, cool. So if the underside does not fully separate from the car, then yes, I should be in good shape. But to some people, my 2008 Corolla would be a really nice car. Like high school me would have loved that car, right? I had nothing. But at a rich high school, that would be viewed as insufficient. So a student of average SES for their school, we have no idea what that means. The good news is that we can find out what the contribution of this variable would be by adding that to the model, and that'll be the next step. But we're just focusing on what happens at level 1 for right now. Okay, so WCSES is what I'm abbreviating this new variable as, within cluster SES. Relative differences in SES only. That's going in as a fixed effect here. Yeah, I've got R output after that. I am saving I am using the saved results for the amount of intercept variance from the previous model and residual variance at level 1 from the previous model so that I can compute pseudo R square. Yes, question?
Any specific reason why in the equation you put the socioeconomic status for the person before the equation you're subtracting the
This one?
yes.
Mhm.
Why are you subtracting the person from the cluster and not the other way around?
This one is the cluster mean subtracted from the person.
Yeah, why is not the other way around?
Because what we want is for somebody who has a relatively high value to have a positive number, meaning they have more SES than everybody else. In some contexts, you might want to flip it based on whether you're trying to talk about like agreement or disagreement maybe, or bias in a certain direction. But generally speaking, it would be phrased this way. So level 1 minus level 2. Thanks for the question. So I am saving the results to compute effect sizes, both pseudo R-square and total R-square. I'll show you the numbers for that in just a second using the R output. So in R, I've only added it here. So outside the parenthesis is where fixed slopes go. Inside the parenthesis is where random slopes go. That's the next unit. The same thing is true in Stata. Fixed slopes go right here. Random slopes would go over here. So they show up in 2 different spots. Other than that, nothing else changes. So now we have variance components of 8 and 37, similar to what we had before, actually. We'll see a comparison of that in just a second. The intercept for the model, fixed intercept, is 12.6. That's my expected math score for what kind of person? Intercepts are when all the predictors are 0, right? So this is, a person is supposed to get 12.6 who's like what? What's 0 mean?
Value is the same as the average value for their cluster.
Yep, somebody who is average with respect to their cluster in SES. That person gets 12.6. Now what if I drive the Beamer? What if I have more money than my cluster? What happens to my math? This one's positive. Goes up, right?
2 points up, yeah.
2 points up, yep. So I would say for every unit more SES than the rest of my school, so relatively more, my math goes up by 2.19. Just me. Not my school, just me. So which kind of variance should I have explained by adding in this new predictor? Level 1 people variance, level 2 school variance.
People.
People! Yeah, this is a people thing. Yeah, want to see how much it was? We expect it to be something based on the correlations we saw earlier. Here's my little function. Again, no disclaimers. Use it as is. So the variance components from the empty model, 39 for the level 1 residual variance versus 37. I got 5%. So 5% of all the reasons why some kids have better math that go to the same school has to do with how much SES they have relative to their peers. So this is not 5% of the variance in math. This is 5% of the student level variance in math, specifically. That's what pseudo R-square is. It's per pile. In your homework, I will refer to this as a specific effect size because we're focusing on each variance component and how effective the model is in capturing it. So 5% of the student variance in math has to do with student differences in SES. Now here's a negative sign. We don't love that. What happened at level 2? We started out with a random intercept variance that was estimated to be 8.61, and after we explained some of the student level math variance, it went up 8.67. So that's why R-square is negative. It looks, at least on the surface, that we made the model worse. However, this is a natural conclusion and not a problem. Do you remember do I need to get the slide out? I can. How we estimate random intercept variance versus true group variance? There's a correction factor. So what happens under the hood here is that we figure out what the actual observed between cluster variances and the means, and then we subtract off how much is due to expected fluctuation and expected fluctuation is indexed by level 1 residual variance divided by level 1 sample size for that group. And so whenever we explain some of the level 1 residual variance, the level 2 variance is going to go up. Has to. They're yoked together like this. Not a lot, and the extent of it will depend on how many people you have in your clusters, but it's going to happen. So in an analysis write-up, if I were to fit a model like this and talk about it, I would just focus on this effect size, and I wouldn't mention the other one because it's not intended to be changed. It's only changed as an artifact. Total R square then. How do I get that one? Do you remember that one? I'll give you a hint. Total R square is computed the exact same way it is in single level regression. Okay, I'm going to call on the TAs then. Erica, tell me how to make a total R square. Yeah, I take my predicted values and I correlate them with the real values, and that's R. And to get to R square, I square it. Yeah. Now one more word I want you to add in: predicted values from what? The model fixed effects, random effects, or both? Fixed effects. That's the one piece here. So we are computing essentially a y hat from the fixed effects in the model only, not from the random effects. That would be cheating if it were from the random effects too. So then this number, I can say 4.4% of the variance in math is explained by this predictor. It represents 5% of the variance in level 1 math specifically. R square gets tricky. Adjectives matter. Question?
Yes, a good one, Lisa. This is related to something that I asked you a couple of weeks ago, but
Okay.
in this model, our intercept right now, the model intercept, is that related to the cluster means in any way? Because you said that that would be the expected outcome for a student, for the average student.
In this current model, the intercept is not conditional on cluster mean anything. So it's for any cluster.
Awesome, great.
And
Okay.
for that reason, some folks would criticize this model as being incomplete because we've allowed for differences at level 1, we have not allowed for the corresponding differences at level 2. And I would agree with that. But why I did this one at a time was so that I could make the point as to what happens at level 2 in terms of the variances, that they will go up because the level 1 variance has been reduced. But yes, not conditional on cluster anything yet.
Yeah, so that intercept is not related to cluster means yet.
Well, it's the expected cluster mean, but it's not expected for any particular kind of cluster, I would say. It's still agnostic as to
Yeah.
which one it is.
Okay, yeah, yes, that was my question, because in the formula we consider the fixed intercept is always a level 2 thing.
Mm-hmm.
So it should be always related, its interpretation should be related to cluster mean something. But in this case it's weird because we only have one level, one thing.
Yeah, so this is what's weird about this notation scheme, and this is honestly something that I've argued with other like methodologists about in papers and stuff.
Yeah.
I like to argue with people, kind of feisty that way. If you just look at this like on paper, these are all level 2 things, right? But I would argue that like this slope right here is not a level 2 slope. It's in the level 2 equation, but it trickles down to multiply a level 1 variable. So to me, that is a level 1 slope.
Yeah.
So slopes to me come in 3 flavors: cross level, level 1, or level 2. And like cross level ones you can think of as level 2 in the sense that they're going to be in this level 2 equation as well. And in certain software packages, all of the slopes end up in the level 2 output, even though they're supposed to be in the level 1 output. So it gets confusing as to what levels are. But to me, because this is multiplying a level 1 predictor, it's a level 1 slope.
Yeah, that makes sense.
To me.
Thank you.
No, thank you. Okay. Now let's fix it. So we decided this model was a little bit weird because we introduced SES at one level and left it out at the other level, even though we know that it has information at both levels, right? You're frowning. Thinking?
There should be tracking 0.
I'm sorry?
You're subtracting 0.
I am subtracting 0. Yes, that face is correct for subtracting 0. Why did I do that? He's like, I got nothing. To remind you that you need to do something here is the answer. This is a placeholder for, hey, if your level 2 predictor doesn't have a mean of 0, stick a number here. That's why it's here. But you're absolutely right that this makes no never mind, as they would say. That driving home the point that ordinarily level 2 means will not have a mean of 0. You would want to pick a number so that it's a representative school of some kind that makes sense. So I am adding in gamma 01, not to be confused with gamma 10. I know, they look like they should be synonyms or something, but they're not. They're the opposite of each other. Do you want to go through the subscripts again? Why they are the way they are? Or someone want to tell me? Why is this gamma 01?
That's for the person 0 and closer 1.
It is close. It's something is 0. What does this 0 refer to? It's not a person. Yeah, it's because this term is predicting beta 0. So if you look at the pattern, everything in this level 2 equation starts with a 0. Because they're all talking about what happens to beta 0. And then this is a 1 because this is the first level 2 predictor of beta 0. Likewise down here, this is 1O because now we're predicting beta 1. So anything else that would be added to this equation would start with a 1. And this is like the jumping off point for where that equation starts, so it starts at 0. So we have the same variable here that I'm indicating I used to center at level 1 is now a predictor here, and it could be potentially rescaled so that 0 means something. That part doesn't really matter for interpretation purposes, for the slopes at least. Okay, so now what do we have? Let's look at the numbers. This is data output here, just in case. We have, I want to play fair across the two. So 12.68, that's my fixed intercept. What is that the reference math score for? What kind of person, what kind of school?
Person with the same score as the school average.
That's right, someone whose SES is average for their school. And what kind of school do they go to?
The Beamer one?
The Beamer one. I'm not actually sure what a mean of 0 means. But if it were a really well-off district, then maybe a mean of 0 would be the Beamer school. But yeah, whatever 0 means is the answer in this metric. Because we subtracted 0 here, meaning that this score would be when this SES goes to 0, which happens when it's at 0. So we can say this is the expected math score for the average student in the average school with respect to SES. That's what I could say. Now, what happens if I have more money than my peers? My math goes up by exactly the same number it did in the last model, 2.19. Yeah, because I've just introduced an uncorrelated level 2 predictor that's got its own job to do at its own level. Yep. So for every unit more SES I have than other people in my school, my math goes up by 2.19. Now this one, for every unit average SES my school has than other schools. That's what a 1 unit change means in this variable. For every unit average SES in my school, the whole school's math goes up by 5.86. The whole school. So this is a level 2 slope that differentiates high-performing from low-performing schools with respect to math. And it looks like, yeah, having 1 more unit of average SES is pretty good for you. Your school's math average goes up by like 6. Within a school, though, 1 more unit of SES than my peers results in a difference of only 2.2. Question?
Is it possible for someone like in the school belongs to a school, that cluster make him or her the score higher by 5.9, and then also within, like the person is more wealthy, more money, also have like 2, so the total will be 7 point something.
So the question was, can we add these two things together? So yeah. So if you are adjusting a predicted math score from being in a wealthy school, then you get your bump of 5.8 or whatever per unit. And then from there, if you have more money than everyone else in your school, you get another bump. So these are per unit bumps, but yeah, you can think of them as additive components of how you get to a math score based on the level 2 standing and the level 1 standing of a predictor. Yep. So which variance should my new cluster mean SES capture? Level 1 people variance or level 2 cluster variance? Level 2. That's what shouldn't happen. Okay, skipping some stuff for now since we're about out of time. I want to show that result. We'll go down to the R code that has it. So this is a comparison across models. Intercept is the top line, residual is the bottom line. So here was the change from just adding within SES. Intercept variance went up a little bit, residual variance went down a little bit for this net change. After adding in between cluster information about SES through the cluster mean, my random intercept variance went all the way down to 2 something. So that is a change relative to the empty model of 0.69 and a change relative to the within only model of 0.694. So if it were up to me, what I would report is relative to the empty model, because it's like this one went down a little bit and then it came back up, and so the change looks a little bit too high. I would enter them both at the same time in practice because each of them has their own job to do. Within cluster tackles level 1 variance, between cluster tackles level 2. So I would report them at the same time and talk about them at their respective levels. And then R square change for total R square functions similarly. We went from 4% from having only the level 1 variable all the way up to 16% by adding the level 2 for a change of 12% across those. So 16% of all the variance in math, period, has to do with SES. Of that, right, so 16% in math, like overall put back together again, total R square. But then, to be more specific, of the 18% that was school level to begin with, school level SES captures 69%. And then of the remaining 82% that was student level, only 5% of that has to do with SES. So SES looks like it has a lot more to do with level 2 than level 1 in this example. Okay, how we doing? Okay enough? So where we're headed next is, what if we had just used grand mean centering instead? Did it the way that most folks would do without knowing any better. Things won't go well, but that will take more than the minute we have left to explain. All right, questions or comments? You're like, we're full. I'm good. Thank you. Good then. Thank you for being here. Let me know if you need anything. Finish up your homework. And what do you have for next? Oh, you have a quiz. You have a formative assessment open. Erica's going to do that one, right? Okay, so you got to read the questions. Tell me what you're going to say. Okay, she's got you covered. All right, see everybody Thursday. Let me know if you need anything. Bye for now.